Okay, good morning, everyone. Uh, any questions? Good morning, Brian. Any questions? Please put your question on chat and before we proceed to the new material. Good morning. For question 29, how would you justify the answer? Okay, also for... Very good. Okay, so I will be looking at two problems that you guys gave me, number 29 and 42. Okay, I will read them and we will discuss them. All right. Number 29, the question is a basic variable. I'll try to put it here, see if you guys can see it. Okay. A basic variable in a linear system is a variable that corresponds to a pivot column in the coefficient matrix. The answer is yes, there is nothing to justify here. The answer is yes, just by the definition itself, by the way we did things. So you have nothing to justify. A basic correspond to a pivot column, which is absolutely true. Nothing really to justify in this particular question. Okay, number 42. I will do 41 and 42. All right, and then we will proceed. 41 asks you the following question. A system of linear equation with fewer equations than unknown, so we have less equation than unknown, is called an indeterminate system. So if you have less equation than unknown, we give the system a name, we call it indeterminate. The question is, let us say the system is consistent, so we don't have that issue. Explain why there must be infinite number of solutions. Okay, so this is number 41, and then we go to number 42. So 41, we have the following scenario. Consistent system, it means we have a solution. Consistent, that's what's given to us. So it means there is no leading in the last column of the augmented. Of the augmented matrix. So that's what's given. It's consistent and less equation than unknown. Unknown. Okay, that's an idea that will be recurring to us in class. So we have so you're thinking about 3x4 system. Think about 2x3 system. Think about 3x5 system. That's really what they are talking about. And the question is why the system has infinitely many solutions. Okay. All right. Who would like to tell us? It's not a hard question. Who would like to tell us why it is the case? So it is consistent and you have less equation than unknown. It has to have a free variable because less equation than unknown. So this is the system. We know that there is no leading here, no leading. And we have, let us say, 3 equations, but at least we have 4 unknown. So the number of leading is strictly less than the number of unknown. It means one of the variable has to be free. And we know that there is no leading here. So if we have 3 leading, they have to be in the coefficient matrix because there is nothing here. That's of the consistency. Is one of the variable is free, hence infinitely many solutions. Okay, so whenever we have, if the consistency is guaranteed, less equation than unknown, we always have infinitely many solutions. Now, number 42 is asking you the following. I'll read it slowly. Give an example of an inconsistent, indeterminate system of two equations and three unknown. So we have that, we have infinitely as long as, okay. So I want an example of, it's a 2 by 3 system. 2 by 3 system, 2 number of equation, 3 number of unknown, which is inconsistent. That's what we want. Who can give me example of a 2 by 3 system which is inconsistent? Okay, I'm listening. Ideas. Who can give me example of 2 by 3 system inconsistent? Okay, I will write what your classmate told me. So Kyle is suggesting this x1 plus x2. I think it's they want a 2 by 3, so we want 3 unknowns. Okay, I will play a little bit with your classmate equal 4. And then he told me, okay, your other equation equal to 5. All right, so he gave me very, very natural, very, very interesting system. So that's 2 by 3. Definitely, this is inconsistent because there is no way you can have x1 plus x2 plus x3 equal to 4. At the same time, x1 plus x2 plus x3 equal to 5. So definitely, we cannot have in 3 numbers that satisfy this equation and this equation. So this is definitely inconsistent. That will do. Any other questions? What about a 3 by 2 system? 3 by 2 system. Give me 3 equations, 2 unknowns. Who can give me example of a 3 by 2 system? Let's see what I want. Okay. A consistent 3 by 2 system. So this is probably number 43, I think. Something I've also assigned. Give me an example of 3 by 2 system which is consistent. And a unique solution. Who can think of a 3 by 2 system? 3 equations, 2 unknowns. It is consistent and it is unique. Okay, Haley, no, that's not, no, okay. So very different. This is 2 by 3. Now I want 3 by 2. Okay, I will take up, so x1 minus 3x2 equal to 5. 2x1 minus 5x2 equal 10. And 3x1 minus 9x2 equal 15. Okay, Haley, why the system is consistent and why the solution is unique?
When I reduced it to echelon form, I got the matrix 1, negative 3, 5, 0, 1, 0, and then all zeros.
Wait, the first row.
Oh, 1, negative 3, 5, 0,
Yes.
1, 0, 1, 0, and then all zeros.
Absolutely correct. Geometrically, what did she actually give me? Geometrically, that's a line, and a line. So geometrically, she gave me the example of 3 lines that intersect at one point only. That's really what the geometry of this is. So if you draw this line, they're going to intersect right here. And if you solve, the solution is going to be 0, 5. 0, 5, which is it's going to be somewhere here. So she gave me example of 3 lines that intersect only at one point. Absolutely correct. Okay. All right, so today we are going, so this is system that, as I said, that we will be working with it throughout the semester. So today we are going back to linear combination and span. So let me start reminding you what a linear combination. We started this last time. You guys have this written down. I just remind you the definition. So let's do that. So let us recall the following. Suppose we have a bunch of vectors in Rn. Remember, vector in Rn, it means nothing more than a list of n number. Don't really, algebraically, that's what it is. So don't be afraid of it. A linear combination of those vectors is any vectors of the form C1, V1. It means you take every vector and you scale it. Then you add it to a scalar multiple of the second vector. You add it to the scalar multiple of the other vector. Those constants C1, C2 are scalars, it means number, and we call them weight. So that's what a linear combination. And then I gave you the following problem. I gave you two vectors, and I asked you to give me three linear combination of u and v. So nothing more is that you take the first vector, you put a scale on it. That's what a linear combination, minus 3 times v. That's a linear combination. And the weights are C1 is 2 and C2 is minus 3. Another one, you can give me u. And this case, the weights are the one that's 1u, and you can think of this plus 0v, and C2 is equal to 0. And there are 100 of them. I mean, infinitely many of them. You can give me square root of 2 times u minus v. And then the first one is square root of 2. The second is minus 1. So that's what a linear combination of. Question number 2 is, we also took the definition. Suppose I have a vector b here. Let's see which vectors I'm going to be working with. Suppose I have a vector b, any vector b. Suppose it is 0, 7. And the question is b a linear combination of u and v? What does this mean? It means, can you put a weight on u and the weight on v, so when you add them, you reach the vector b? So my second definition was the following. So let v1 through vk and b be vectors in Rn. We say that b is a linear combination of v1 through vk if we can find weight C1 all the way to ck such that b is a linear combination of those vectors. It means such that b could be written as C1 V1 plus etc. ck vk. Or another way to write this, or if the following equation has a solution. Now, when I see an equation, it means I'm talking about equality between two quantities. And if the equation has a solution, it means we should have unknowns. It means the unknowns here are going to be the weight. So it means if this equation has a solution, it means if I can find those unknowns. All right, so let us see immediately an example of that. As I said last time, if I go fast, you guys cannot write, let me know. But this is from last time. So now, example. Suppose u is the vector 2, 1. So it's a vector in R2, so we can view it as the point 2, 1, and v minus 3, 2. And b, the vector 0, 7. The question is, show that b is a linear combination of u and v. So what I'm asking you about, it means we need to find. So show that it is a linear combination. It means we need to find weight C1 and C2 such that C1u plus C2v equal to b. These are the unknowns. I always emphasize that what we are solving for are the C1 and C2. Okay, so can we find those? So this is equivalent to solve. It means this is equivalent to solve the following equation. Equal to b. All right, so let us try to solve it. So what is the u? means C1 times 2, 1 plus C2 times minus 3, 2. So right now I am solving for the weight, 0, 7. Okay. So what does this mean? Okay, what does it mean to scale a vector and add them? C1 times 2, 1, it means, so I will do the first problem fairly slowly. Plus means we have to find such that this is equal to 0, 7. So we're solving in the most natural possible way. So this is equivalent to do the following. It means adding vectors means adding component. Means we need to find C1 and C2 such that to C1, I'm adding now the component equal minus 3C2 equals 0, and C1 plus 2C2 equals 7. So I want constant so that this vector equals this vector. But two vectors, so this is occur when two vectors are equal if they have the same entry. So this occurs when 2C1 minus 3C2 equals 0, and C1 plus 2C2 equal to 7. Okay, so finding C1, C2 then, so solving this equation right here is really boiling down to solve the system. So solving this vector, we will call this a vector equation in a second. So solving this equation really boils down to solve the system. So now how do we solve a system? Whatever system we have, how do we solve it? So we're going to solve the system. Okay. Now, how do we solve the system? Now, of course, that's an easy system. It's a 2 by 2, but we will do it the way we've been learning how to do it. So I immediately take the augmented matrix that correspond to the system. So let's see what the augmented matrix is. 2 minus 3, 0, and 1, 2, 7. Okay, so now we are in the process of solving the system. Now, that's a system I need to solve. At this stage, I forget, it's back to what we've been doing. So if I am to solve the system, the first thing I will do, I will switch rows just to have a 1 here because make our life easier. 2 minus 3, 0. So I switch the rows. I don't have to, but this will make things easy because 1 is always easy to work with. So this is my first leading. And then I have to create 0 beneath it. So this will give me the following. 1, 2, 7, 0, minus 2 plus 2, 0, minus 2, minus 4, minus 3, minus 7, and minus 7 plus 0, sorry, minus 14. So I can stop here if I want. I will do probably one row operation and then I stop. So this is equivalent to, I'm going to divide the last row by 7 just because, by minus 7 just because I can. So minus row 2 divided by 7 will give me 1, 2, 7, 0, 1, 2. I can stop right here. Or you can go to the reduced echelon form. It's a very easy system. You have your choice. So what does this mean here? What does this mean? What are we solving for? We're solving for the weight C1 and C2. So this means that the second equation read C2 equal to 2. So now we are solving for the weight. The first equation read C1 plus 2C2 equal to 7. Back substitution will give me C1 equal 7 minus 2C2. It means 2 times 2 minus 4 is equal to 3. So this means that, so what are we solving for? So this means that The vector B can be written as 3 times U plus 2 times V. These are the weight I am solving for. Okay. Let us analyze what we did and a little bit of terminology after that. So let us really analyze the situation. Any questions so far? I'm going to take you back to what we did. Let us check, actually. Let us check. I mean, am I doing it correctly? So it means if I take 3u plus 2v, do I get the vector b? So let me bring this down and let us check. If I take 3 times this vector and I add 2v to it, do I get the vector 0, 7? Okay, 3 times 2, 6. 6 minus 6, 0. 3 times 1, 3. 3 plus 2 times 2, 4. 3 plus is equal to 7. So at least my answer is absolutely correct. Now let us go and analyze a little bit what we did. Okay. So we need to find those weights C1, C2 such that the linear combination will give me the vector B. Okay, so C1 times 2, 1. We set it up plus this equal to 0, 7. So let us watch that. This is C1. The coefficient of C1 are basically the entries of the vector U. And the coefficient of C2 are basically the entries of the vector B. So when we solve this vector equation, we actually boil down to solve the system. But let us observe what is the augmented matrix of the system. What is the augmented matrix of the system? The coefficient of C1 were the entries of the vector U. So in the augmented matrix, the first column is going to be actually the vector U because these are the coefficient of C1. The coefficient of C2 are the entries of the vector V. So this is the vector V. And the constant term are nothing more than the vector B. So trying to find the weight C1 and C2 such that B is a linear combination is really boiling down to solve a system, that system, while the augmented matrix of the system are the first column is the vector U, the second is the vector B, V, and the last column is the one I'm going after is the vector B. So let us write this as kind of a terminology and a process. So terminology. Okay. Please, if I'm going fast, it's your job to tell me to slow down or ask question or tell me I haven't seen something. So terminology. The equation, I will just give the terminology for 2 vectors. The same idea hold for k vectors. So the equation first. C1U plus C2V equal B is called a vector equation. A vector equation. Equation because we have equality. Vectors because we have equality between vectors. 2. And that's the remark about this idea right here that I've talked about. Solving the vector equation. C1U plus C2V equal to B is equivalent. So solving it means solving it for the weight. Is equivalent to solve the system. With augmented matrix, so solving this really boils down to solve a system where the augmented matrix is The first column is U. The second column is V. The augmented column is the vector B itself. And the solutions of the system are the weight. The solutions of the system are the weight. All right, so go over it one more time. This equation will be called vector equation, and solving it is boiling down to solve the system where the augmented matrix are U, the first column, second column V, and the augmented column is the column that I am after, is the one that I want to show it as a linear combination of U and V. And the solution that we get are called the weight of the linear combination. Now, before we take more examples of those kind of problems, I'm going to go and try to talk about how to view this geometrically. Okay, so we're going to talk a little bit of geometry, and we're going to say, how can we visualize B a linear combination of U and V? So let us listen a little bit to geometry. It's easy to do it in R2. It becomes very hard anywhere else. Even in R3, it becomes hard. So let us talk about the geometry. Okay, so I still have my vectors I'm going to be working with are the one I've been working with, 2, 1. And V is the vector -3, 2. And my goal is how to visualize that the vector B, which is 7, 0, is a linear combination of U and V. All right. So what I'm going to do is the following. I'm going to try to draw as clearly as I can. So I'm going to take R2 here, and I'm going to draw the following vector, 2, 1. So suppose this is 1, 2, 3, 4, 5, -1, -2, -3, -4. Okay, the vector 2, 1, so that's it, 2 here and the 1 right here. So that's my vector 2, 1. And then I'm going to draw the vector -3, 2. 1, 2, 3, that's a -3, 2. 1, 2. And then because I want to add, I'm going to take, this is my U and this is my V. Okay, so this is U here and this is V. Okay, and my vector B is -7, 7, 0. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So this is my vector B, which is 7, 0. Okay. And now to explain this concept, B linear combination, I'm going to use a little story if you want. Let us say we have the following scenario. I'm going to take the line here that carry the vector U. So that's one line. And I'm going to take another line that carry the vector V. So these are my 2 lines. And I'm going to use the following scenario. Suppose you have an ant or any object, like a little robot if you want. A robot wants to go from the origin from 0 to B. So imagine the following scenario to understand the linear combination. I have a robot, a little robot. I want to start from 0 all the way to B. I want to go from here to here. And the question is the following. This robot wants to go to B following 2 directions. So following the direction of U and V. What do I mean? The direction of U and V. Okay, so a robot wanna go from here to here following the direction of u and v. It means the robot can only move parallel to the vector u, so parallel to this line, or parallel to that line. So it cannot zigzag the way it wants. And the question is, can the robot do that? So if we can understand the scenario, we understand at least linear combination in R2. Okay, so this is my u here, this is my v. My robot wanna go from here to here. And it has two choices. So imagine that there are two streets. Robot gonna go from here to here, but he can only move parallel to U and parallel to V. So he can move this way and he can move that way. He cannot move any other way. Can the robot go from 0 to B? What do you think the answer would be?
Yes.
Yes, of course, yes. Yeah, how is gonna go? So it's gonna go a little bit like that, a little bit. And then when he keep eyeing B, when he start feeling that he can go parallel to V, he start moving. So if I wanna do it accurately, I will do it like that. From the point B, I'm gonna take a line totally parallel to V, absolutely parallel to V. Okay, and then let's see how the robot will go. It will go 1U, it will go another one, it will go this one, and then it start going V. So if you have one direction of V and another direction to that. So the vector B now, geometrically, I was be able to write it as a scalar of the vector U plus a scalar of the vector V. And if I had very, very good markdown, very good scale down here, we can see that this vector here is from here to here, that's my 3U. And from here to here, this is my 2V. And that's what we got by doing it algebraically. So is B a linear combination of U and V? Is basically asking yourself, can you go from 0 to B by scaling a little bit U and scaling a little bit V? And the answer is absolutely yes. Is it a little bit? That's really the linear combination geometrically. How you can reach a vector by moving in two directions, which are the U and the V direction. Right. So let me ask you another question before I move on and do algebra. Let me say I take a vector W. So suppose I take W to B, so B, and purely algebraically, geometrically, I don't want to do algebra for that. So suppose I take W to be the vector -4, 1. -4, 1. And the question geometrically, is W a linear combination of U and V? Geometric, I don't want the algebra. What do you think? First, let me draw the vector, -4, 1, 2, 3, that's a -4, 1, that's 1 right here. And my vector, let me use the red for it. So this is the vector right here. Okay, that's my W. What do you think? Can I write W as a linear combination of U and V? Imagine the robot wanna go from here to here. The robot has two directions. He can follow two lines, either the line parallel to U or parallel to V. Can he do it? What do you guys think? Jackson tells me yes. Anybody else tells me yes. Anywhere in R2, exactly. You can go anywhere in R2, but we're gonna see that at the end of the lecture. So the idea is that from here, I can take a line parallel to V, like that. And then how is my object, the robot? A little bit in the direction of -U. As you realize, it's gonna go in the direction -U, and then a little bit in the direction of V. And then we hit the vector W. But he has to move in the direction of -U, not +U. So geometrically, we can actually visualize the idea of a linear combination, especially in R2. And as your classmate said, we can go anywhere. I mean, even if I take a point here, I will be able to reach that point following the U and V direction, which is an idea, of course, we're going to talk about it a little bit later. One more example of linear combination, and then we move on. So I would like to do one more example here. Oh, sorry. Okay, I think I forgot to write it down. Okay, so example number 3 or whatever. So I took example all in R2. Now I'm going to take an example in R3. So let me take U to be the following vector. In R3, it means the vector have 3 entries. 1, 5, 0. And V the vector 2, 5, 2. And B the vector 4, 6, 2. And the question is B a linear combination? Is B a linear combination of U and V? Okay, can I find weight on U and weight of V so that when I add those, can I scale U and scale V so when I add them, I reach the vector B? I don't know. Since I am in R3, the picture become a little bit obscure to us. So this is equivalent to, so we need to solve, so basically it's equivalent to solve the following vector equation. So we're gonna solve C1U plus C2V equal to B. That's what you have to solve. Okay. So this is equivalent to solve the following. So if we were this vector equal to the vector B is 4, 6, 2. This one is C1. I'm adding them quickly, plus 2C2. So I'm adding basically the vector. And that's what give me, let's see, 5C1 plus 5C2. And finally 0 plus 2C2. Okay. And the question is, can I solve the system? All right, so this is equivalent to solve the following system. C1 plus 2C2 equal to 4. 5C1 plus 5C2 equals 6. And 2C2 equal to 2. Okay. Now we can basically stare at it and solve it, but still I want to go back to the augmented. All right. So the augmented. The first column has to be 1, 5, 0, because these are where the coefficient of C1 are coming from. The second column is V, 2, 5, 2. So, and the last column is the B. So let's make sure C1 plus 2C2 is 4, 5C1 plus 5C2 equals 6, and this is equal to 2. And let us solve the system. So that's a system of 3 equations with 2 unknowns. So this is going to give me 1, 2, 4. That's my leading. Everything below it has to be 0. That's going to give me a 0. And then this will give me minus 10 plus 5. And this would give me minus 20 plus 6, which is going to give me minus 14. And this is 2 and 2. Okay. Please, if I have any questions, any stupid algebra mistake, let me know. So now we gonna move here, create a leading, and use this leading to make this into a 0. Now, because this is much simpler, I'm going to divide the last row by 2. And then, so let me do that. Just to make this, the math a little bit simpler. I will have 0, minus 5, minus 14, 0, 1, 1. Finally, I'm going to switch just to make life easy for me. 1, 2, and 4. Okay, now we are almost ready. This is my leading. This is my leading. I want to make this into a 0, and the algebra is easy now. 0, 1, 1, 0. 5 minus 5, it's a 0. 5 minus 14, which gives me minus 9. Okay, what does this mean? Immediately, so what can you say immediately? Immediately, what can you say? Absolutely inconsistent. Inconsistent because the last row read so we have a pivot in the augmented matrix, definitely inconsistent, 0 equal to 9. Okay. So what does this mean in terms of our problem? So we try to find C1 and C2, and we reach an inconsistency. What does this mean for my original problem? It means there is no way I can write B as a combination of U and V. So there is no way I can stretch U a little bit, stretch V a little bit, combine them, and get the vector B. So it means that B is not a linear combination of U and V. Okay, so I am in R3. I have two vectors. I have a third one. I'm asking myself, can I write it? And the answer, no, we cannot write it as a linear combination. Okay. And I will try a little bit to explain this geometrically. When we hit R3, it becomes a little bit harder, but I will try to explain this geometrically. Okay, please questions before I move on. Okay, let's see how can we visualize this situation geometrically. Okay, here we are. So these are my vectors. I'm going to try to draw them the best I can in R3. And then I'm going to let you think about it a little bit. 1, 5, 0. So that's going to give me 1 from here, 5. So this is my vector here. That's my U. My vector V is 2, 5, 2. So 2 from here, 5 from here, and then we're going to go up by 2 units. So let us imagine this here. So this is my vector V. So this is my U, and this is my vector V. Okay? And the vector B is somewhere here. Somewhere here is the vector B. Okay. We realize that B, I cannot stretch U by a little bit, and I cannot stretch by V to get B. B is not a linear combination. I wanted to look at the picture a little bit. Can anybody tell me anything? Why do you think this is not happening? I'm going to help you a little bit. I'm going to take the following plane. So I'm going to take the plane. Yes, I'm going to take the plane that contains 0, it contains V, and it contains U. This is the plane because 3 points form a plane. I'm going to take this plane. Any vectors, which is a linear combination of those two, if I take any vector, it's a linear combination, it means the vector is obtained like this. You start from 0, you stretch U a little bit, and then you go a little bit in the direction of V. So any vector which is a linear combination has to be inside this plane. There is no way out. So if B is not a linear combination, it means the vector B from here to here means this point here is not in the plane P. So B is not, and that's really what's happening geometrically, is not in the plane P. Okay, that's the geometry that's happening in R2. So any vector that's a linear combination of U and V is, as I said, you start from here, you stretch a little bit U, you go in the direction of V. So this vector have to be in the plane that contains 0, U, and V. It can't be anywhere else. So this means that B is not in that plane. So that's the geometry of these examples. Now, when I hit R4 and so the geometry definitely is not there, but that's to give us a little bit idea what's happening in this picture. Right. Now we are going to talk about something called the span. So first, let me tell you what's going on. So span. So before I defined it, as usual, accurately, I motivated a little bit. So span. SPAN. So suppose I take two vectors. So any two vectors, suppose I take Q to be, let us say 150, and V252. Nothing special about my vectors, just bunch of vectors. Okay, and the question is, how many linear combination of U and V can we form? Linear combination of U and V can we form? Okay, it means how many vectors can we get by scaling Q and scaling V and add them? Simple question. Don't be afraid of the answer. How many linear combination of U and V? One, two, three, infinitely many? Infinitely many. Yeah, of course. Let us start list some of them. Suppose I take 2U. Is this a linear combination of U and V? Of course, it is. We're stretching U by a factor of 2, so that's a linear combination. Okay, we just take U and stretch it. Another linear combination. 2U. So every time I do that, I'm creating a new vector. So when I'm taking 2U, that's a new vector, which is a linear combination of U and V, where the weight on V is 0. 2U plus V, that's another new vector, which has have different components, so it's a new vector, but it is a combination of U and V. Okay, and I keep going forever. I mean, I can put the 0 vector. Is the 0 vector a combination of U and V? What do you think? Yes, because how can you write the 0 vector as a linear combination of U and V? What are the weight? I want more answer. Haley and Jackson are asked. I want everybody to answer. So it's 0U plus 0V. So that's definitely another linear combination. So how many linear combination I have? It means how many vectors I can produce, which are a linear combination of those two. I can produce infinitely many vectors. The collection of all those vectors that we can get by a linear combination of U and V have a name and called the span of U and V. So the span of U and V is lots of vectors, but each one of them is a linear combination of U and V. So that's what we call the span. So let me define it now rigorously. All right, so now we defined the span rigorously and then we work with it. So definition. Let V1 through Vk be vectors in Rn. So it means each one of them have n entries. The span of V1 through Vk, so it's a new set, it's a new collection of stuff. And we use this to denote span, open parentheses, V1 through Vk, close parentheses, is the set of all vectors in Rn that are a linear combination of V1 through Vk. So suppose I am in R3 and I have only two vectors. Their span is a whole set of vectors, but they are specific ones. They are obtained as a linear combination of them. So in either word, what's the span of V1 through Vk? It's the set of all vectors of the form C1 V1 plus C2 V2 plus CK Vk. Very specific type of vector. Not everything is in the span. They have to be a combination of those two. So what does it mean for a vector to be in the span? A vector be in the span means that B is a combination of those vectors. Okay, so I take two vectors and I take everything that I can get as a linear combination. I call those the span of those two vectors. Okay, so let us do an example of that. Okay, any questions before I move to examples? Okay. The first example, only to understand the definition, and then we're going to try to get a little bit deeper in our understanding of the span, slowly. So my first example is the following. Suppose I have the following vectors, v1, v2, v3, and the vector b. So these are my vectors. So I am in R3 now, but I have so many vectors, the geometry actually is hard to visualize. That's why we're going to do everything algebraically now. So I have 1, -1, -2, v2, 5, -4, -7, v3, -3, 1, 2. And I have the vector b, 0, -1, -1. Question is b in the span? So even if I don't write this, is b in the span? It means we have to understand what this means. It means, can I get the vector b as a linear combination of those vectors? That's really what it is. And then my answer question is, if so, it means if you can do that, write b as a linear combination. If you can't, you can't. All right. So let us answer this question. As I said at the beginning of the course, this course is a lot of terminology. And the only way you can understand it if to understand the terminology. So every time I ask you a question, my advice to you is not just to write an algorithm, just try to remember, what does it mean be in the span? So is be in the span? So question number 1, it means don't start writing matrices, write the definition. Is be in the span? This means is, does, the equation. That's what it means. Means can I write B equal B has a solution? So before you write equation, because you will be immediately lost, ask yourself, what does the span mean? It means can I write B as a linear combination? That's what you have to justify. So it means equivalent to do the following. C1 times this plus C2. When you write the definition, you start understanding the concepts more and more. So that's equivalent to solve the following. 1 -1 -2, 5 -4 -7, -3, 1, 2 equals 0, -1, -1. So that's equivalent to solve this vector equation, which means equivalent to solve the following. As you realize, I'm going back to basic all the time. So if I add the first vectors, I will get here C1 plus 5C2 minus 3 equal to 0. I'll get minus C1 minus 4C2 plus this minus 1 minus 2C1 minus 7C2 plus 2C3 equal minus 1. So it means it's solving, finding those weight equivalent basically to solve the system. So this is equivalent to solve the system. And minus 2C1 minus 7C2 plus 2C3 equal minus 1. So finding the weight is really equivalent to solve the system. Now we take the augmented matrix, which is we know exactly how it should look like. So the augmented matrix, and then we proceed. The augmented is 1, -1, -2. That's the V1, which is exactly what we got here. And then the 5, -4, -7. These are where the coefficient of C2 are coming from. And -3, 1, 2. Those are the coefficient. And then finally, the augmented term, which is the B vector. Okay, so now we have to solve. And if the system is consistent, it means B can be written. If it's not consistent, it means B cannot be written. It means B is not in the span. So let us solve this. I use my pencil because I do mistakes, algebra mistakes. So this is going to be equivalent to. So let us do the augmented. Okay, I have a 1 in here. I'm going to make this into a 0 and this into a 0. So I'm going to add row 1 to row 2. And that would be my new row 2. And 1, 5 minus 3, 0, 0, 1, minus 2, minus 1. Now I'm going to make this into a 0. So I take 2 times the first row plus the third row. That's going to give me my row 3. I have a 0 in here. I will have a 3. Please be careful with my math. Minus 6 minus 4. And that's 0 minus 1. My 1 is guaranteed. Move to the right, move down. I have a leading. Now I have to make everything under the leading to be, again, a 0. So I have to take 3R2 plus R3 into R3. So I will have 1, 5, minus 3, 0, 0, 1, minus 2, minus 1, 0. Sorry, I have to multiply by minus 3. Minus 3 plus 3, it's a 0. Minus 3, that's a 6. 6 minus 4, it's a 2. Minus 3, that's 3 minus 1, it is a 2. Okay. And now my question, is B in the span? Yes or no? Yes. Why? Because the system is consistent. We don't have any issue. So if the question is B in the span? Once you reach here, you say system consistent because I don't have any leading in the augmented term. System consistent, hence B in the span. It means it can be written as a linear combination. So if the question is B in the span, once you know that the system is consistent, you're done. However, my question is B in the span? And then I'm asking you, if so, write it as a linear combination. So at this stage, I'm asking you to solve the system. So part 2, we're going to write B as a linear combination. For that, we need to solve. So for that, we need to solve for the weight. Okay. All right, we can solve. We can do 2 ways. We can stop here at the echelon form and then do back substitution. Or we can go back and reduce to the reduced echelon form, which is sometimes easier to do. So this is going to be equal to, I have 2 and 2. I make my life easier by dividing the third row by 2. The third row by 2. And this would give me 0, 0, 1, 1. And then 0, 1, minus 2, minus 1, 1, 5, minus 3, 0. So I guaranteed those 1. And I'm going to go to the reduced echelon form this time. I don't have to, but as a practice. So for reduced echelon form, we start from the bottom and we work our way up. So 0, 0, 1, 1. I'm going to make this into a 0 and this into a 0. So I'm going to make the third row, I multiplied by 3, added to the second, which gives me 0, 1, 2 minus 2 is a 0, 2 minus 1, it's a 1. And then for the first one, I multiplied the third row by 3, added to the first, will give me 1, that's a 5, 3 minus 3 is a 0, and this gives me a 3. Okay, so I'm almost done. So this is a 1, This is a 1, this is a 1. One more step, and I have my reduced echelon form, and the solution will be staring at us. So 0, 0, 1, 1, 0, 1, 0, 1. So now I need to make this one into a 0. So minus 5 R2 plus R3 into R3. And this would give me 1. Minus 5 plus 5 is 0. And 0. Minus 5 plus 3, which is a minus 2. So now we are ready to solve. So this will give me the following. The last row tells me that your C3 is 1. I'm solving for the weight. The one before it tells me that C2 is 1, granting I didn't do any algebra mistake. And the last one tells me that your C1 is equal to minus 2. So now this is the vector B. I can write it as minus 2 V1 plus V2 plus V3. Means I can reach the vector B by going minus 2 times V1, then I add to it the vector V2, then I add to the vector V3, and I reach the vector B. So I can write it. Dylan, is that R1 and not R3? Where, Dylan? I didn't see where. Which line? Dylan, I cannot. Right here. Okay, sorry, mine plus R1 into R1. Thanks. Thank you very much. All right, any other questions? Okay, so now let us start a little bit understanding the span. Slowly, we have to understand it. So algebraically, we know how to show a vector is in the span. Now we have to start understanding the span of some vectors. So today I'll start with 2 scenarios. Scenario number 1 is the following. Okay. Span a little bit geometrically. Oops. Okay, we're going to try to understand the span geometrically. So I start with the span of one vector, and then I move on to 2 vectors, and I will touch upon 3 vectors probably next time. All right, so first, span of one vector. So what's the span of one vector? So suppose I have U any vector. Suppose U is a non-zero vector. So what is the span of U? Okay, algebraically, the span of U is all linear combination of the vector U. Means all vectors of the form okay, what are the form of a vector? If I have one vector U, one vector, what's a linear combination of one vector? It means every scalar multiple of this vector. That's what a linear combination of one vector. So if I have one vector, it means all vectors of the form C times U, where C is a scalar. So algebraically, that's what's the span of U. So example, before we do the geometry, which is going to be easy. So for example, have U, these are vectors in the span, 2U minus U, and of course the 0 vector, because the 0 vector can be written as 0 times U. So now let us sketch the span. So assume my vector is in R2, in R3 it will be the same. This is my U vector right here. It's non-zero. And what are all the linear combination? Okay, the 0 vector is a linear combination. Half U is in the span. So every time you take the vector U and you start scaling it, you are within the span. So 2U minus U minus 2u. So every time you take the vector u and you scale it, you're actually going to create a new vector in the span. So what's going to be the span of the vector u? What are all the vectors that could be written as a scalar multiple of u? So what's going to be the span of u? Geometrically. The line, exactly. So the span of u is going to be any vectors on this line. It means any pair of any list of two numbers which lies on this line. So the span of u, we're going to write that's going to be the line that passes through the origin and u. Okay, so it's nothing more than the line through the point that go through the origin and the point u. Now, even here, I'm thinking q, I'm writing the vector notation, but I'm thinking of u as this point right here. So every line is all the points on the line that passes through the origin and u. Anything here is a scalar multiple of u. If I take a point here, there is no way I can, if I take this point right here, there is no way this could be a scalar multiple of u. Ask the question. So everything here is a scalar multiple. So for one vector, the span is the line. It goes through the origin and u. Okay. Now span of two vectors in R2. So part 2 is span of two vectors in R2. Okay, start a new page. Of two vectors in R2. I will start with very simple scenario and then, actually, the whole thing is simple. We've almost done it by now, but let us talk about it. So first example, what is the span of the following very specific vectors? I'm going to take the vector 1, 0 that you guys called the I vector in 261 and 0, 1, what you guys call the J vector. All right, what's the span of 1, 0 and 0, 1? So go to the picture right here. Okay, 0, 1 is that one. So this is 0. This is my vector 1, 0. And this is the vector 0, 1. The span, it means everything that could be a combination of those two. So let me ask you a very straightforward question. Suppose I take the vector 3, 2. Okay, is the vector 3, 2 a linear combination of 1 and 0? Yes or no? If yes, give me the linear combination. If no, tells me why no. Can I write 3, 2 as a scalar times 1, 0 plus a scalar times 0, 1? What do you think? Right. Anybody else besides Rodriguez? Absolutely correct. So what's 3, 2? These are the component of the vector. So it means I can write it 3 times 1, 0, obviously, plus 2 times 0, 1. In this course, we will not use I and J. I will introduce something else. So because we work in Rn. But this idea is the same, but the notation will be different. So the vector 2, 3, absolutely, it's a linear combination. So if I take any vector AB, so suppose AB is any vector in R2, any vector. Can I write it as a linear combination? Of course, A could be written A times 1, 0, whatever the vector is, plus b times 0, 1. So any vector in R2 can be written as a linear combination. How we express this mathematically? We express this mathematically by saying that the span of those is equal. Watch the notation, equal R2. Okay, so what does equal R2 mean? Equal R2 means if you give me any ordered pair of numbers, AB, I can write this ordered pair as a linear combination of the ordered pair 1, 0 and the ordered pair 0, 1. So when I say this is equal R2, it means you throw any vector at me in R2, it means any list of two numbers, I can write it as the linear combination. That's what we mean equal R2. So this is really very simple because all of you can see that. Now suppose I take other two vectors. So suppose I ask you the following, and this is what we hinted on at the beginning of the lecture. Suppose I take the span of the following two vectors. The one I started the lecture with 2, 1 and minus 3, 2. Okay, it means I take any vector that's a linear combination of those two. So this is the problem, I think. That's the one I took at the beginning. 2, 1. That was my first vector, and minus 3, 2. And this is purely geometrically now. Okay. And the question is, if I take this vector B, can I write it as a linear combination of U and V? I will treat this question today geometrically. Next time I will treat this question purely algebraically. But now geometrically, can I write B as a combination of U and V? Remember the robot which is moving? Absolutely. This is my vector B. I go a little bit this way, and then a little bit in the direction of V, I have my vector B. If I take a vector here, can I write it as a combination of U and V? Of course, we can. From here, I can take the line parallel to V. I move a little bit in the direction of minus U, then in the direction of V. So this could be written as C1U plus C2V. The C1 is negative because you go opposite to U, and the C2 is positive. And geometrically, I can do that anywhere. Suppose I have a vector here. Can I write it? Of course. From here, I take a vector parallel to V, and then I'm going to move a little bit in the direction of U, a little bit in the direction of V. So if I call this vector, whatever, I give it name Z vector, Z is C1U plus C2V. The C1, is it positive or negative? Is the C1 positive or negative? Look at my picture. C1 has to be negative. It's the weight I put on U2. The C2 is also negative. This should remind you almost the four quadrant in R2. So the B here, C1, C2 positive. If the vector here, C1 negative, C2 positive, both of them negative, here one is positive, one negative. So this definitely should remind you the four quadrant that we talk about in regular XY plane. So any vector in R2, any list of numbers here, I can write it as a linear combination. It means this is going to allow me to write equality here, and this will allow me to write R2. So that's geometrically, meaning any list of two numbers, anything in R2, I can write it as a combination of those two, which is something you guys alerted to at the beginning of the lecture. Okay. Next time, we're going to take this problem again, but we're going to show it algebraically. All right. Okay, I have to stop right now. Any questions before I let you go? All right, have a great rest of the day. Please do the homework for next time. Please make sure you do the homework. Okay, bye-bye for now. Bye, guys.